Hey guys, in this video, I'm going to give you an introduction to arrays and a quick overview of how memory works. And this video is going to be split into three parts. First of all, I'm going to cover the basics of arrays, and this part is going to be pretty basic, so if you're already familiar with arrays, don't worry about watching this part. And in the second part, I'm going to cover what memory is as opposed to storage. And finally, I'm going to cover how integers and integer arrays are stored on memory. Arrays and memory are two of the fundamental topics in data structures and algorithms, so let's get started. Okay, so first of all, what is an array? An array is basically a collection of items of a single type. So an example would be this one, which is an array of integers, or this one, which is an array of strings. And it's not usual for an array to have multiple types. So it's not usual for us to have something like this, where this array has both strings and numbers inside. And let's take a look at some code snippets in C here to see how you can use arrays in practice. I'm only going to take a look at C here, but it's going to be pretty similar to other languages too, like Java. This line, int sample array square brackets 5 equals 246 and so on, says create a new array with 5 integers and then populate it with the elements 2, 4, 6, 8, and 100. And you can visualize this array as a box with 5 partitions because this array is able to contain 5 integers. If you want to change some of the elements in this array, of course, you can use code like this. The first line says change the first item of this array to 20, and then the second line says change the second element of this array to -5. So after executing these two lines of code, sample array will look like this. You can see that the first 2 elements have been changed, but not the other 3 elements. And of course here, the index of the array starts at 0 instead of 1. And it's not necessarily the case with all the languages, but this is what we're going to use throughout this course too. Now, what if you already have 5 numbers in this array, and you wanted to add 2 more numbers, let's say 2 and 3, after the 5th item? You might say, well, why don't you just add 2 more partitions at the end of this array and then put those numbers in there? But actually, you can't do that. And to understand why that's the case, why you can't add more partitions at the end of this array, I'll need to give you a quick overview of how memory works on a computer. Okay, so what is memory exactly? For me to explain what it is, the first thing you'll need to understand is that there are mainly 2 mechanisms for storing data on your computer. The first one is memory, or it's sometimes called RAM, and the second one is storage, which has different types, for example, a flash drive, hard disk, or a solid state drive. Now, the biggest difference between storage and memory is that the data on storage is permanent, while the data on memory is not. What I mean by that is, if you think about your laptop, when you turn off your laptop, the data on storage will still be there, but the data on memory will disappear as soon as you switch off your laptop. So if you think about the bunch of photos you have on your laptop, when you turn off your laptop and turn it back on again, they should still be there, right? And that's because they're on storage and not necessarily on memory. So like I said, the data on memory, on the other hand, just disappears when you switch off your computer. Have you ever had an experience where you started working on an essay or you started drawing something on your computer and then suddenly you just lose all your progress because your computer crashes and then it shuts down? And that's probably because those documents were on memory but not necessarily on storage. So when you work on those documents and when you hit the save button, that finally becomes a file on your computer on storage this time, so that the next time your computer crashes, it's still going to be there. So at this point, you might say, wait, why do you need these 2 separate mechanisms then? Why can't you just store everything on storage? Well, the thing is, reading data from and writing data into storage is pretty slow. It's sort of like walking all the way to the file cabinet you have in the basement to retrieve, the files there, whether they're photos or documents. It is necessary sometimes because that's where you have those documents, But if you do it too often, it's just going to take too much time. And that's actually where memory comes in. Memory is sort of like a temporary desk you have in your room. So once you retrieve those documents, from your storage, whether they're text documents or photos, you'll be able to put them on your desk or on your memory. And once they're there, it's going to be so much faster to work with them. And the reason it's so much faster is because it's so much quicker to write data into and read data from memory than it is with storage. And then once you finish working with those pieces of data on your memory, once you finish editing them and modifying them, then you can bring them back to your storage so that you can save them there more permanently as computer files again. So that's the gist of how memory and storage work together with files. And the way they work together for applications is actually pretty similar. So when you have applications on your computer, they're stored on storage originally. And you can easily tell that's true because when you turn off your laptop and turn it back on again, those applications are still going to be there. But when you launch one of them, let's say Google Chrome, it's going to be loaded onto memory so that it's faster to use and faster to access there. And so if you start running too many applications at the same time, they're all going to be loaded onto memory, and you might actually start running out of memory space. And that's why, that's one of the reasons why running too many applications at the same time on your computer might actually slow down your computer. And let's now see how this whole thing actually looks on my computer. Since I'm using a Mac, if you want to get an idea about how much memory I have, you just need to click this Apple icon and then about this Mac, and you can see that I have 8 gigabytes of memory here. And what about storage? For storage, I have 251 gigabytes. And actually, one feature of storage is that it's usually much bigger than memory. And actually, on the Mac, there's a way to get a rough idea about how memory is being consumed. You can just open Activity Monitor. I think there's something similar for Windows too. And here you can see that, for example, Dropbox is using about 240 megabytes of memory, and Google Chrome's using about 100 megabytes of memory. And what happens if I go to Chrome and quit this application? It should stop consuming so much memory, right? Let's see if that works. I'm going to quit Google Chrome, and it's no longer here. Now, how is all of this related to programming, and in particular using arrays? To understand that, let's take a look at this piece of code in C. This line int a equals 1. When you compile and execute this line, of course, a variable called a is created, and the integer 1 is assigned to that number. And this integer 1 is stored on memory and not on storage. And that means that when you turn off your computer after executing this code, this integer 1 will just disappear because everything on memory, of course, disappears when you turn off your computer. But how is this integer stored on memory exactly? For me to explain that, you'll need to understand two things. The first one is that each integer, when it's stored on a computer, it's often expressed as 32 ones and zeros. So for example, the number 1 can be expressed as a bunch of zeros and then 1 at the end. Actually, that's 31 zeros and then 1 at the end. And the number 2 can be expressed as a bunch of zeros and then 1 and then 0 again. That's actually 30 zeros, 1 and then 1 0. And just like that, pretty much any integer that you might encounter in real life, whether they're 100 or 200 or minus 223, each of them can be expressed as 32 ones and zeros. Now, each of these zeros and ones is called a bit. So a bit is either 1 or 0. So we say each integer can be expressed with 32 bits. And you don't have to worry about how it's converted exactly if you don't know about it yet, but just know that pretty much any integer within a reasonable range can be expressed with 32 bits or 32 ones and zeros. Okay, the second thing you'll need to understand is a simple model of memory. Memory can be thought of as a long tape of bytes. Now, what is a byte? A byte is basically a small unit of data, and it consists of 8 bits. So each byte might look like this, where it has 8 bits, or this one. Now you can visualize the simple model of memory along tape of bytes like this. So this is the long tape, and each of these compartments represents each byte. So you can sort of imagine a bunch of bits, 8 bits to be exact, being crammed into each of these compartments. And then you can store bytes, which are of course small units of data, in these compartments to represent anything you want to represent on your computer. Now your computer needs a way to find any particular byte very easily, and you want to be able to do that because you want to be able to do things like store 2 bytes in these 2 compartments and then store 4 bytes right after that, and maybe retrieve 2 bytes from the first 2 compartments. And your computer achieves it by assigning an address to each byte, and each of those addresses is represented by a single integer. So in this hypothetical example, we have the address 120 for this byte and 121 for this byte, and so on. At this point, you might say, wait, why do we have these particular numbers, 120, 121, and so on, representing the addresses for these bytes? Well, the answer is, I came out with this arbitrary number, 120, to represent the starting address for these bytes. But in reality, you don't have to worry about it. And you don't have to worry about it because the operating system determines what the starting address will be for your particular application. So basically, the operating system, whether it's Mac or Windows, decides what your application should live over here in memory, and then someone else's application, let's say Google Chrome, should live over here, and so on. But the important thing to understand here is that even though the starting index 120 is arbitrary here, the way you have consecutive addresses, 120, 121, 122, and so on, that's exactly like a real system on your computer. Anyway, like I said earlier, each integer can be represented with 32 bits. Sometimes, depending on the environment, it's stored with 64 bits instead, but let's just say 32 bits for now. And the question I have here for you is, how many bytes do you need to store each integer? Well, that's pretty simple because you have 8 bits in each byte. So if you have 4 bytes, you can store 4 times 8 bits, which is 32 bits, which is just enough to store each integer. So how can we store an integer on memory? You might say, wait, why don't you just take 4 bytes, the 4 consecutive bytes right here, and then use that to represent an integer? And that's exactly what a real computer does. So in this particular case, when you have int a equals 1, 1 is first of all converted into 32 bits, zeros and ones, and those bits will be split into these 4 bytes, and then they're going to be stored right here on those 4 bytes. If you have one more integer, for example, int b equals 3 right after this line, that variable will be stored on those 4 bytes right after the first 4 bytes. So that's how integers are stored on memory, but actually the idea is going to be the same for things like decimals or characters. You might need a different number of bytes to store each different type of data, 2.3 or A or whatever, but the idea of using consecutive bytes to store each piece of data is exactly the same. Anyway, what if you wanted to store an array of integers instead of single integers? To see how that can be done, let's take a look at some more code in C here. And let's say just like before, we have int a equals 1, then that integer a, or 1, will be stored, let's say, in these 4 bytes from 120 to 123. And let's say right after this line, we have this line, int sample array square brackets 3 equals 5, 3, and 20. This array will actually take 12 bytes right after the first 4 bytes, so that's from 124 to 135 right here. And we need 12 bytes because we need to be able to store 3 integers. So that's, of course, 3 times 4 equals 12 bytes. And the first number 5 will be stored in the first 4 bytes. So that's from 124 till 125. 127 right here. And the second number 3 will be stored in the 4 bytes right after that, naturally. So that's from 128 to 131. And then 20 will, of course, will be stored in the last 4 bytes right here. Now, the question we asked ourselves earlier was, why can't we just add 2 more numbers, let's say 1 and 2, to the end of this sample array? If you look at this model of memory, it looks like we'll be able to just allocate 8 more bytes over here and then use those 8 bytes to store these 2 integers. But actually, you can't do that. To explain why you can't just do that, why you can't just allocate more memory, allocate more bytes right after this array, I would actually need to explain a little bit more about how memory works exactly, but let me give you a more simplified argument here instead. The simplified argument here is that after this line, after allocating 12 bytes for this array, we don't know what's going to be right after that in this memory space. So for example, you might have this line, int c equals 4, right after this line. In that case, this number 4 would be stored in these 4 bytes from 136 to 139. And when you store an array, you need a bunch of consecutive bytes. And that's basically why you won't be able to just add more bytes to this array. And actually, if you wanted to still add 2 more numbers to this array, what you would need to do is you would need to create an entirely new array, over here in memory. And you would need to make that array longer than the original array, let's say length 5 instead of length 3, and copy over these numbers one by one to the new array. And you would probably create this array dynamically. And this word dynamically is important, but if you don't know what it means exactly, don't worry about it for now. And then if you wanted to add even more numbers, let's say 3 more numbers to the new array that's longer than the original array, then you would actually need to create a new array again, which is even longer than the second array, and then copy over all the elements to the new array again. So you might think this whole strategy is a little bit awkward because you need to keep creating new arrays and maybe keep deleting the old arrays, but that's actually what's used in practice often. So if you wanted to create sort of a resizable array, a kind of array, a kind of new array, you might say, that can accommodate as many elements as you want to put in there, this is one strategy for doing that. So for this, resizable array, you can initialize it as a small array, let's say 10 elements. And then when you want to put in the 11th element, you can make a new array that can accommodate, 20 items instead, and then copy over old items to the new one. And then keep going like that, 20 elements, 40 elements, and then length 80 and so on. And this is actually the essence of how many sort of resizable arrays work in different programming languages. So for example, in Python, you might see, the Python list, and in Java, you might have used the array list. They might not look like resizable arrays when you look at them or when you use them, but actually, if you look at the source code, if you, sort of look inside the hood, that's how they are implemented. Okay, so this was actually a somewhat simplified explanation of these topics, arrays and memory, and you'll be able to actually start using them to start building more complex data structures that you're going to learn throughout this course, like hash tables and trees. And by the way, when I was doing some research for this video, I actually used this video's sponsor's website a lot, and it's called Brilliant.org. So for my research, I was using this computer memory course. And the section I use the most is called Linear Memory Model, which is in the Introduction to Memory chapter. This Linear Memory Model section basically gives you a more detailed picture of what I explained in this video about memory, and it comes with a bunch of practice problems too. Like I said in my last video, applying what you've learned through solving problems is a good way to solidify your understanding of the topic. And personally, I found that going through this section helped me refresh and solidify my understanding of how memory works. And this linear memory model section actually assumes that you're already familiar with binary and hexadecimal numbers. So if you want a quick refresher on those, I'd get started with the previous section instead. and that one is called binary decimal and hexadecimal. If you want to check it out for yourself, you can go to brilliant.org/csdojo. Okay, as always, I'm YK from CS Dojo. Thanks for watching, and hopefully you can keep what you've learned in this video in your memory as well as your storage, I guess. Anyway, I'll see you guys in the next video.